Okay, hi everyone. So today we'll be talking about the trend in the boiling point of hydrides down groups 14 to 17. And this is a part of the chapter 4.4 of IB chemistry, which would be the intermolecular forces of attraction. Okay, so here we have a very popular graph that I believe all of you guys have seen before. And in this case, um, the question would be to explain the trend that is seen in the figure on the right. So we are going to address the whole graph and every part of this graph. Okay, so to answer this question, you have to ask yourself four sub-questions. Okay, the first one being, why do the groups 15, 16, and 17 period 2 hydrides show an exception in the trend of boiling points? And the second question is, why does water have a higher boiling point than hydrogen fluoride and ammonia? The third question is, why do lower hydrides in group 15, 16, and 17 have an increasing boiling point down the group? And lastly, why do the group 14 hydrides show no exception in the trend? Okay, so the first question, why do groups 15, 16, and 17 period 2 hydrides show an exception in the trend? So if you look at these three molecules, you should be very familiar with them by now. So that is because all of them would have hydrogen bonds, okay, which is much stronger than intermolecular forces such as London dispersion force and dipole-dipole forces. Okay, so as a result, because of the hydrogen bonds that are present, okay, there will be a higher boiling point that is experienced by these molecules. Okay, but for the lower members, okay, they display much lower melting point and boiling point, and that is due to the fact that they only have forces that are a lot weaker holding these molecules together, right? Dipole-dipole and London dispersion forces, which if you place them on a relative scale, okay, hydrogen bond would be maybe 10, while on the other hand, for the LDF and dipole-dipole, they are just at maybe 1 to 1.5. Okay, so there's a huge difference in terms of the strength, and that's why you see such kind of trend. And the second question that we asked ourselves was, why does water have a higher boiling point than the hydrogen fluoride and ammonia, right? So in the case of water, okay, you see that it has two lone pairs as well as two delta plus hydrogen atoms, right? And that's crucial for intermolecular hydrogen bonding to form. So as a result, in the case of water, you can form two hydrogen bonds on a lone pair on average. Okay, but comparatively, you can only form about one hydrogen bond in hydrogen fluoride and ammonia. Okay, you can think of this like a limiting and excess idea. So if you look at hydrogen fluoride, you've got three lone pairs, but you've only got one hydrogen, right? So the number of hydrogen atom is severely lacking compared to the number of lone pairs. And as a result, the number of hydrogen would be determining the number of hydrogen bonds that are formed. Then on the other hand, for ammonia, you've got three delta plus hydrogen atoms, but you only have one lone pair. So it's going to be the same result, which is that the number of lone pair is going to determine your number of hydrogen bonds formed, which is just one, right? But in the case of water, you have 2 lone pairs and 2 hydrogen atoms. So 2:2, everything is so-called equimolar, right? So you have the most extensive hydrogen bond in water, and that must give rise to the most energy required to overcome these hydrogen bonds, right? So therefore, water will have the highest boiling point in them, right, which is 100 degrees Celsius. Okay. All right. So, but we still have to explain, the difference between the hydrogen fluoride and ammonia, right? Both of them would only have one hydrogen bond, but for the hydrogen fluoride, it's got a boiling point of 19.5 degrees, whereas for the ammonia, it is 33 degrees on the negative scale, right? Okay, and this is, of course, due to the fact that fluorine is a lot more electronegative than the nitrogen. So as a result, okay, you have a stronger hydrogen bond that's formed in the hydrogen fluoride compared to ammonia, right? And just for your reference, fluorine would have a value of 4.0 on the Pauling's scale of electronegativity, whereas for nitrogen, you only have about 3.0, right? Okay. So that explains the difference in terms of the boiling point in the 2 molecules. Okay, so moving on to the third question. Why do the lower hydrides of 15, 16, and 17 have increasing boiling point down the group? Okay, so the first thing you have to know is that these are still polar molecules. Okay, but they will have a decreasing net dipole down the group because the central atoms are getting less electronegative. Okay, so the permanent dipole is going to decrease. Okay, the dipole-dipole forces are going to decrease, but okay, there is an increase in the size of electron because there are more and more electrons down the group. Okay, so there will be an increase in the strength of London dispersion force while the dipole-dipole forces are dropping. So on one hand, you have a decreasing dipole-dipole forces. On the other hand, you have increasing London dispersion forces. Okay, and which one is more? In this case, we see that the increase in London dispersion forces is actually outweighing the decrease in the dipole-dipole forces. And as a result, you will see an overall increase in the overall intermolecular force of these hydrides down the group, right? And as a result, you will need more energy to overcome these forces. And so there will be an increasing boiling point down the group. Last question was, why do the group 14 hydrides show no exception in trend? And of course, the first thing you must know is group 14, they share 4 electrons in their valence shell. Okay, so they all will have a tetrahedral shape, which is something like this. Right, so this is a tetrahedral shape. Okay, and of course you know that all the bond angles are going to be 109.5 degrees. Okay, this is something that you have to know in IB. All right, but that's besides the point. The main thing is because they are all tetrahedral in shape, and because all the bonds are the same in each molecule, So you have equal dipole that's created, right? Okay, that's going in each of the 4 directions. So as a result, because of this identical bond, so there will be a cancellation of dipoles. So overall, there will be a 0 net dipole, and therefore all the group 14 hydrides are non-polar in nature. Okay, so because of this non-polarity, okay, there will be only one type of intermolecular force present. Okay, there is no hydrogen bond for sure. There will be no dipole-dipole. There will only be London dispersion forces. Okay, and again, this is dependent on the size of the electron cloud, which is increasing down the group, right? There are more electrons down the group, so the size of electron cloud has to increase. Okay, so down the group, you have increasing electron cloud size, so greater LDF, and more energy will be needed to overcome these forces. And therefore, boiling point will just increase down the group, and there will be no exception because there is no other forces apart from LDF. All right. And with that, thank you for watching the presentation, and I hope to see you again.